Alright, welcome to this video where we're going to talk about traversing trees, in particular binary trees, though the traversal methods that we're going to look at here can be generalized and applied to any kind of tree. So to do that, I've got an example tree here, and that's what we're going to do our traversals on today. But I do want to start by talking a little bit about different kinds of traversals. Why do we need to talk about traversals? So first of all, when we're looking at a simple list, like a linked list, there are very standard traditional ways of traversing it, namely end to end. You start at one end and go to the other. And so there's not a lot to talk about when you're talking about traversing a list. Other ways, randomly going through the list, seem a little bit strange, and so we don't usually use them. Whereas when you get to a tree usually has one end that's pretty obvious, the root, but the other ends, there's a lot of them, and so there's no straightforward end-to-end sort of traversal that you can do. There's one fixed end and then a bunch of dangly ends, if you will. There's more than one way that we can approach that problem and try and visit all of the nodes in the tree. And actually there's several different ways, and there's sort of two broad ways that make sense. And the two broad ways are called the depth first search and the breadth first search. And we're going to actually focus mostly on depth first search, so I'll just comment slightly about breadth first search before putting it behind us. A breadth first search is a fairly straightforward method where we just go basically level by level and then on each level left to right. So in this case, if we did a breadth first search of this tree, it would just simply be A, B, C, D, E, F, G, H, I, J. So in order, you can see that's probably how I labeled these nodes when I constructed this tree. That search is very useful in a lot of algorithms, but we're not going to look at it at a lot of detail in this video. Instead, I'm going to push that off until we start looking at graphs in more detail. Instead, we're going to be looking at depth first search. Now, what a depth first search does is it kind of follows the edges in our tree, meaning if we started at A, it's going to keep going deeper and deeper down this branch until it gets to the end. In that sense, it kind of is like an end-to-end traversal. We start at the root and we try and go as deep as possible. That's the depth first part, as deep as possible into that tree. Now, with our depth first search, we're going to look at three different kinds called the pre, in, and post order traversal. So to do that, I want to then emphasize what is going on in our tree. And maybe I'll just go back to our example here to talk a little bit about that. Well, if I'm trying to visit every node in my tree, why am I doing that? Usually there's a purpose. What is it that I'm trying to do to the tree? And there's usually a couple obvious things. One is maybe I'm just trying to output it. I'm just trying to say what's in my tree. So I'm going to go to each node and output it in the same way I might do that for a list. Well, in addition, on top of that, I might want to do something to each node. Maybe I'm going to operate on, I'm going to change it in some way. Or maybe what I'm doing is like a search. I'm just checking each node to see if it has a property, and then if it does, maybe I'll do something to it then. So in all these cases, I'm going to call this the operation, or to operate on the current node. Check it, display it, modify it, do what I'm going to do to it. But once I'm done doing whatever I'm doing to this node, I have two other things I might need to do. I need to traverse down its left path, or traverse down its right path. Now remember, in a linked list there's only one path, so you just go to the next node. But for a tree, even the simplest tree, a binary tree here, we have this question of which path am I going to go down. So we do still have a convention going left to right as a standard when reading English. We're also going to impose that in our traversals. Go to the left node before we go to the right node. If we do that, that gives us three possible locations where we can place the operation. We can do it first. Right when we get to the node, we operate, and then we move. We traverse left or right. this is pretty standard. This is probably the way you would do it in a linked list traversal. As you get there, you operate, and then you move. Well, because you don't usually come back in a linked list. Well, in these depth first search traversals, these are typically implemented recursively, meaning if we go down the path, we're going to come back up as well. And so here we can operate first, but we could also operate after one of these traversals when we return from the recursive call. So that gives us the option of also operating between the two calls. We call this the Inorder traversal, or after the two calls, and we call this the Postorder traversal. So I do want to do an example of this on our example tree here. All right, so in my example here, I'm going to indicate as I go which node that I'm going to visit as I visit it. Now, because this is the pre-order traversal, as we visit the nodes, we actually, as soon as we get there, we output it. So this is, in some sense, the easiest one. So we'll take a look here. First, of course, we start at the root. So A is output first, and we go left first. So we output A, then we go left to B, output B, then we go left to D, output D, then we go left to H. And then here, we output H, we try and go left, there's no left, we try and go right, there's no right, and here's where the recursion unwinds us back to D. And then D will try and go right, there's no right, so its recursion will unwind or backtrack it back to B. Now B will try and go right to E, and again, E being a leaf, no children, it will recurse back to B. B now finished will recurse back to A, and A will go to C. C now down its left to F, F down its left, but there is no left, so it goes down its right to I. And then we recurse back. I back to F, F back to C, and now C down its right to G, and now our G down its right to I. So we can see that the order that we would output here would be A, B, D, H, E, C, F, I, G, J. This would be our pre-order traversal of our tree. Now in our in order and our post order, I'm going to have to keep distinct in my mind when I visit the node and when I output the node, which is going to be different. Okay, so to do that, I'm going to look here at, again, my yellow indicator is going to be when I visit the node, but just because I visited the node A doesn't mean I've operated yet. I go left immediately, and I go left and then left again. Now H, I go left again, but there is no left, so when I return from that attempted call, here's where I operate and output. So I'm going to use red here to indicate that I've now output H. So now I return from H and I output D, and I try my right. Again, there is no right, and I recurse up, so I'll output B now, and now I will recurse right. There is an E. E tries its left, there is no left, so then it outputs. Then it tries its right, there is none, so it recurses back to B. B is now done, so it unwinds back to A, and A calls down now, or sorry, A now operates and returns its value. It will now call C, and C immediately calls F because it's its left child. F now tries its left child, does not exist, so it does operate and output F. It will now traverse to I, and again I has no children, so it will try its left, operate, that is output, then try its right and recurse back. F now finished will also recurse back to C, which will output, and try its right, G. G will try its left before operating, but there is no left, so it will output, and then try its right. And again, J, as a leaf, will operate, and we will continue to unwind here from J to G to C to A before the traversal finishes. So again, this order, if we read it out again now, the first output was H, D, then B, then E, then A, then F, then I, then C after that backtrack, then G, and then J. So this would be our in-order traversal. Let's try our last traversal now. This one has to be the post order, where we operate only after traversing left and right. So hopefully your intuition's being built up now. And think to yourself, what's going to be the last node that we're going to output? Well, we go think about that. So again, we're going to visit A first, but we're going to traverse both left and right. So we're going to go left, and same thing as before. You'll notice in all these traversals, we visit the nodes in the same order. They all do the left to right depth first search, but they operate on the nodes in different orders. That's the distinction. So now H again is still going to be the first one output because it neither has a left nor a right, but it will try its right before outputting now. Same thing here with D. We'll return to D, but it will try its right before outputting. It will output though because it has no right. So now when we go to B, we see it tries its right, which is indeed it's E, and then we try, and sorry, E is a leaf, so it outputs, and then, only then, when we recurse back to B, does B output as well. We get to A, and A tries its right first. C tries its left, F tries its left, there is none. It tries its right then, there is one. I now, a leaf, has no children, so left and right fail before it outputs. It recurses back to F, and it now outputs. We return back to C, but C tries its right. And G tries its left, there is none. Tries its right, J. Okay, J tries its left and right, there are none, so it operates and returns. G now is done, so it returns. C returns, A returns. So we see that backtracking very clearly. And again, in this one, our order will be H, D, E, B, I, F, J, G, C, A. Okay. So I want to, now that we've taken an example of that and had a chance to look at that, I want to show a little trick on how we can actually do this a little quicker. Okay, so to continue this example, what I want to do now is look at first the path that all of our traversals take through the node. So again, they're all going, what I said, left to right, but our depth first search. Okay, so in so doing, this envelope I've drawn around here is actually the path that our recursive calls will take. And we'll go down the left one, and then there's some backtracking that happens, but again, we'll go down each branch, backtracking before returning back to the root node. Now this path shows us the path we take in all three of our traversals. Remember, they all follow the same one. They all just output at a different point. So to do this, what I want to do is I want to show here a trick we can use to calculate our traversals if asked to do this, say, as an exam question or on an interview question possibly. Now say I want to do a preorder traversal. To do that, I'm going to go to each of my nodes, and I'm going to draw a tick on the left-hand side of the node. And now, if I want to record the preorder, I just visit the nodes in the order of my envelope now, and whenever this line crosses my tick, I output. So we get A, B, D, H, coming down here, back up, it looks like we get to E, coming around we have C, F, I, back up here, looks like we have G, and J. And there's a trick for each of them. So now, if we go ahead, oops, let's do it here, and draw a tick on the bottom of each of our nodes, we can get the in-order traversal. So again, reading it out here, we're going to get H, D, B, E, A, coming all the way back up here. Looks like F, I, C, G, J. Okay, and hopefully you've anticipated now that we can also get the post order by going to the right hand side. Okay, again, reading it through as we go. H is still the first. So we went H going through. Looks like we get D, but now we got E, then B, not A yet, coming all the way around here, we get I, F, J, G, C, A. And indeed, if we go take a look, these are indeed the traversals that we just came up with. So we're good. So this is a little trick. Okay, with this trick, or with this analysis here, it allows us to do a quick, I'm going to do a hand wavy kind of analysis here to say, okay, how many operations, what's a good big O bound for this traversal operation? So any of these traversals. Now, unfortunately, recursive analysis is a little bit beyond what I want to cover in this video here. So instead what I'm going to do is I'm just going to quickly go through and say, look, here's a quick estimate. How many times do we visit each node? Well, given this is a binary tree, we could visit it once when we sort of come in here. Okay. We can visit it once when we come back up in between its left and right child, and then we visit it once on the way back afterwards at the end. So at most, we're going to visit each node 3 times, and there are n nodes. So this math gives us a good estimate that the actual amount of time it's going to take us to carry out one of these traversals is also big O of n time. We're going to visit every node. That makes sense. That's a good lower bound. We have to visit every node. But how many times do we visit every node? At least in a binary tree, at most 3 times. So we get ourselves order n for our runtime of, again, any of the 3 traversals. All right, say this happens. Say you had your tree, you calculated your traversals, but then all of a sudden, boom, you're gone. No more traversals. What can we do here? Is there a way that we can take these, no more tree. So is there a way that we can take these traversals here and reconstruct the tree that we were looking at? And of course the answer is yes, otherwise why would I have done that? So the first thing we can do is say, well, what was the root of the tree? And no cheating, we know what the root of the tree was, right? But no cheating, this is all we have here. What was the root? Well, if you were paying attention, the root is the first thing that was output in the preorder. It's also the last thing that was output in the postorder. So without too much effort, we should be able to say, the root here was A. Now notice the Inorder doesn't help us. The root is stuck here in the middle. So we can't find out what the root is from the Inorder, but the Inorder is critical and crucial because if we go to the Inorder and we look at it here, what we'll notice is that the Inorder is telling us something here. It's saying these 4 nodes, H, D, B, E, right in here, H, D, B, E, all must be to the left of A in the subtree over here. And these other nodes here, F, I, C, G, J, these ones must all be in the right subtree of A. So the Inorder is actually giving us crucial information. Now I don't want to write it like that, of course. I want to build the tree up, but I can get it from this information here. Okay. Now the other thing I'm going to do is I'm going to go and isolate these numbers off, or these elements off, remembering that each of these 3 traversals will visit the nodes in the same order. So these 4 here are also bundled up as 4 here. They're the next 4 that are encountered in the preorder. And in fact, looking in the preorder, we see here this B here tells me the next node I must encounter must be the B. Okay. And now I can sort of recursively apply this strategy. Now I'm going to go look at these 4 here and say, hey, where's my B? My B is here, and immediately I see an E on the right. I know here there's an E to the right. Okay, it's all by itself, so I don't have to worry about what that tree looks like. It only has an E in it. On the left, I must have an H and a D. Now I don't know what the structure of that is. There's a bunch of different ways it could look with an H and a D. So I do need to go back to the preorder here, find my H and my D, and see, oh, it says D. D is next. D was the next one we encounter. Now we know H is next, but I don't know if it's left or right unless I look here again, and that tells me, oh, it's left. Okay, so that gets me my H over there. Let's see if we can again apply that recursively to the right hand side here. Doing so tells me it looks like the C is first, but finding the C down here tells me it looks like I got F and I to the left, G and J to the right. So nothing I can conclude yet, and without a little bit of work. So let's go back up here on my left hand side and my right hand side here. My left hand side, the first one I encounter, looks like is an F. Okay, F. And we can see here that I must be to the right of it. Likewise here, let's be careful. Okay, in our preorder, our G must be first, but J looks like it's to the right of it. And sure enough, that's the tree that we started with. We could have also used the post order instead of the preorder here. Just going backwards, we can see those values are also isolated here. B being the root, C being the root, so just working backwards. But of course, working backwards usually seems backward, so the preorder is a little bit easier to work with. So if you have the pre and the in, you can recover. And if you have the post and the in, you can recover. But I'm not sure about any other combinations. I don't think with the pre and the post by yourself you can. How about this? Try it out yourself. If you can figure out a way to make it work with the pre and the post, let me know, and I'll make a little video to announce that as well. But for the moment, I'll leave that as an exercise. And I'll also use this point to say, why don't we try one more example of this by looking at, so this one we could have cheated on, maybe come up with this one. Instead, though, I have another quick little example we could have here. So this is another example, could be a good exam or interview question. Say you have two friends, Alice and Bob, and they have their favorite tree, but they've lost it. Luckily, they've saved their traversal. Alice saved the preorder, and Bob saved the inorder. Can we help them out by constructing their tree for them? All right, say we've got ourselves in this situation here. We've got the pre and the in here, and we want to reconstruct these trees to help Alice and Bob. So again, let's follow the same pattern we saw before. We said, okay, 6 must be the root here. Okay, and again, we're going to find the 6 down below, noting that these ones must be on the left, these ones must be on the right. Okay, so isolating them off maybe. Something like that. We can see that 1 must be the first one we encounter on the left. Seeing the 1 here tells us all 3 of these are to the right, so there's no left child of the 1. So all of those, we see 7 must be next then, so if everything's to the right, 7 is the next one we encounter, and we can see pretty quickly here, since it's in the middle there, that we must have a 2 here and a 4 here. Okay, so continuing, we did the left-hand side, let's do the right-hand side. All these nodes must be on the right. The 9 looks like it must be the root. Okay, finding the 9 here. 5, 8 on this side, 0, 3 on that side. We got again the 5, 8 on the left-hand side. We can see that the 5 is first, and here telling us 5, the 8 must go on the right. Again here, now looking at the 0, 3, 0 comes first, and 3 is which side? The right side. here's our tree for that particular problem. Okay, so this concludes the video on tree traversals. It gave us a couple examples of how to compute a traversal given a tree, a couple tricks how to do that, and then maybe how to recover a tree if all you have are a couple traversals for it. And so this is sort of an interesting application. I'm going to leave the video at that. In my next video or series of videos, I'm going to look a little bit closer at the heap data structure, show you the operations related to it, and looking at some of the runtimes related to that as well. All right, thanks for watching, and we'll see you in the next video.